All right, this is problem set number 25. We're going to be talking about mixtures of gases. We're also going to be talking about densities of gases. All right, so what is meant by standard temperature and pressure? So we know that at different temperatures and pressures, the conditions of gases change, right? And so what we want to do is we want to define a certain set of conditions that we just refer to as standard, which will allow us to communicate with one another. It's just something to know. So standard temperature and pressure. Temperature is 0 degrees Celsius or 273 Kelvin. That's standard temperature. And standard pressure is 1 atmosphere. Okay, so you could be given a problem where you're not told the temperature and pressure, you're just told that it's at STP, then you should know your temperature and your pressure. So what's the volume of 1 mole of an ideal gas at STP? Doesn't matter what gas. Let's figure this out. We know that PV equals nRT, and here we're given moles, so we have N, and we're standard temperature and pressure, so we have our temperature and our pressure, and we're trying to find volume. So volume equals nRT over P, 1 mole, the ideal gas constant, temperature is 273, pressure is 1 atmosphere. Plugging these in, I get 22.4 liters. So at standard temperature and pressure, 1 mole of ideal gas will fill 22.4 liters. Does it matter which gas? No, because there's nothing in this equation that specified which gas we were talking about. All right, birds and sailplanes take advantage of thermals, rising columns of warm air, to gain altitude with less effort than usual. Why does warm air rise? All right, so let's think about this. PV equals nRT. If the temperature goes up because it's warm, a defined number of moles of something at a given pressure, what has to change in order, when the temperature goes up? The volume will have to go up. Well, we know that density is mass over volume. If the volume goes up for that gas, what happens to the density? Density goes down. And when the density goes down, that's going to make that air rise above more dense gases, which is going to bring us to the equation for density for a gas that we can figure out. So I'm just going to do that right here. So just make this a little bit nicer. Density equals mass over volume. Well, I know that mass is equal to the number of moles times the molecular weight. So we're going to use big M as molecular weight, right? Because moles times grams per mole gives me grams. So that's mass. Moles times molecular weight. So I'm just going to replace that here. This grams, I'm going to replace it with moles times molecular weight. And then volume, we know in an ideal gas, volume is equal to nRT over P. So nRT over P. Well, this is N times M. Dividing by fractions, the same as multiplying by the reciprocal. And you can see N's cancel, and I'm left with the density equals P times molecular weight over R times T. Okay, that's a useful thing to understand. Doesn't really matter if you can solve it. If you have the equation, you're good. So that takes us to B here. Radon is a naturally occurring radioactive gas found in the ground and in building materials. It is easily inhaled and emits alpha particles in its case. Cumulative radon exposure significant risk factor for lung cancer. Calculate the density of radon at 298 Kelvin and 1 atmosphere of pressure. Let me quickly pull up a periodic table. Okay, so we're trying to find the density. We know that density is going to be P times M over R times T. Well, what's my pressure? My pressure is 1 atmosphere. What's my molecular weight? Well, this is radon, so if I'm on the periodic table, if I find radon, it's down here on the bottom right. 222 grams per mole is the molecular weight. 222 grams per mole. Okay, R value, 0.08206. Liter atmospheres, per mole Kelvin, and my temperature is 298 Kelvin. Do the math. And awesome, when I do that, I get a density of 9.08. What are my units here? All right, atmospheres cancels, Kelvin cancels, moles cancel. I'm left with grams per liter. Is that a density? Yep, mass over volume, right? Grams per liter. That's my density. All right, our radon concentration is likely to be greater in the basement or on the top floor of the building. Well, remember, more dense gases fall. So, let's see. So what is the air that's normally in your house? Well, it's normally oxygen, nitrogen, that type of stuff. What are the densities for oxygen gas and nitrogen gas? Oxygen is like 32 grams per mole. Nitrogen is like 28 grams per mole. How does that compare to this 222? Well, that's a lot smaller. So, and that's the only thing changing. So we'd expect the density of normal air to be way smaller. Okay, so we would say that the density of radon is high compared to air. So that means it's going the radon itself is going to fall to lower altitudes, which means we would expect the amount of radon to be greater in the basement. All right, what's the density in grams per liter of sulfur hexafluoride at that temperature and pressure? Well, density is PM over RT. We got 2 atmospheres, sulfur hexafluoride. So sulfur hexafluoride is going to be SF6. So if I grab the molecular weight here, got S, 32 plus 6 fluorines, which reach 19. I get a molar mass of 146. Oops, 146. And temperature of 227 plus 273 gives me 500 Kelvin. I do that math, and I got a density of 7.12 grams per liter sulfur hexafluoride. All right, density of air is 1 gram per liter at these conditions. What's the molar mass of air? Now remember, air is a mixture of different gases, so what we're finding is the average molar mass of air. But density is PM for RT, but I'm trying to solve for molar mass. If I rearrange the equation, I get molar mass equals density RT over P, which in this case is 1 for the density, 0.08206, temperature is 298. Pressure is 642 torr, but I'm going to divide by 760 to get it into atmospheres. And I get a molar mass of air at about 28.9 grams per mole. Which makes sense, right? We know that air is a lot of nitrogen. Nitrogen's molar mass is 28. Some oxygen, which has a molar mass of 32. So in between those two makes sense. Okay. 26.2 grams of an unknown gas occupies this many liters, that temperature, and that pressure. What's the molar mass of the gas? Further studies indicate that it's monatomic. What element do you think it is? All right, so let's talk about this. It's an unknown gas. We know the volume, temperature, pressure. Anytime I see they give me a volume, they give me a temperature, they give me a pressure, I should be thinking PV equals nRT, right? Knowing that if they give me those 3 things for gas, they have essentially given me the moles in this case. Well, I know that molecular weight is grams per mole. That's what I'm trying to find. What's the molar mass? I know there's grams per mole. They give me the grams, and with these 3 things, they give me the moles. So I can just do grams per mole. So I'm going to find the moles first. N is PV for RT. Again, 742, but I'm going to change it to atmospheres. Volume is 5.3 liters. We got 273 plus 40 is going to be 313, I believe. Okay, so that gives me about, let's see, I got 0.201 moles. And I know molecular weight is grams. I know I have 26.2 grams divided by 0.201 moles. And that gives me a molar mass of about 130 grams per mole. And it says it's monatomic. That means it's just one element, one solo atom, about 130 grams per mole. Iodine's 126.9, xenon's 131. So it's probably xenon. That's what I would say. This last part, which element do you suspect the gas is? All right, partial pressure. This is really where we get into mixtures of gases. What is meant by partial pressure? Well, here's the idea. I know that I have some number of moles. I'm going to say N total, some number of moles in my gas. And if it's a mixture, some of your moles are gas 1, some of your moles are gas 2, some of your moles are gas 3. Let's say it's got 3 things in it. Okay, and all of those moles add up to the total moles. If you think about pressure, what is pressure? Pressure is the idea that I have collisions happening with the wall of my container. Okay, and every collision that happens exerts, these are supposed to be gas particles running into a wall. Sorry if that wasn't clear. Each of these gas particles, when it hits the wall, exerts a pressure on that wall. And all of the gas particles exerting pressure adds up to the total pressure. But if we have 3 different types of gas, so for example, I've got a red gas particle and a black gas particle and a green gas particle, altogether these added up to 3 hits, right? The total hit, 3 total collisions. But one of those collisions was red, one was black, and one was green. So similarly, if let's say red was O2, black was N2, green was H2, oxygen's exerting a certain amount of pressure, nitrogen's exerting a certain amount of pressure, and hydrogen's exerting a certain amount of pressure, because the moles or the particles are all different. So if I'm talking about the partial pressure of gas, just as I have the total moles is just the sum of the moles of each individual gas, the total pressure is just the pressure of each individual gas. And so what we say is this is the partial pressure of gas 1, this is the partial pressure of gas 2, this is the partial pressure of gas 3. Okay, so I'm going to erase this now. As a definition for partial pressure, you could say it's the pressure exerted by one species of gas it's the pressure exerted by one species of gas. Essentially, what would the pressure in the room be if you removed every gas particle except that one that you care about? So we're gonna do some of these calculations. But the thing to understand is that the wall that's getting hit by all of the gas particles doesn't care or doesn't know which type of gas is hitting it. So if in your room 20% of the particles are oxygen, then 20% of the collisions on the wall are going to be from oxygen, and therefore 20% of the pressure is going to be coming from oxygen. So what we can say is my mole fraction, that we do this big X thing for mole fraction, that's just the moles of oxygen, the mole pressure, mole fraction of oxygen, just the moles of oxygen divided by the total moles. It's just what percent of the total moles are oxygen, okay? Well, what we can say is that mole fraction is also going to be the pressure exerted by O2 divided by the total pressure. And so usually how we write this is we usually say that the partial pressure of O2 equals the mole fraction of O2 times the total pressure. In other words, if 80% of the moles are oxygen, then 80% of the pressure is going to be oxygen. Okay? But this would be kind of our equation for partial pressure. So let's jump in here and use it. Maybe my awful explanation will become clear as we start using it. All right, the gas mixture contains 7 grams nitrogen, 2 grams hydrogen, 16 grams methane. What's the mole fraction of H2? Okay, the first question is just to find the mole fraction, this X thing, of H2. Well, we know that the mole fraction of H2 is just going to be the moles of H2 divided by the total moles. So I need to find the total moles and the moles of hydrogen. Well, they give me grams. I need to get to moles. So I know that I have 7 grams of nitrogen, and I know that 1 mole of N2 is 28 grams. So I have 0.25 moles of nitrogen. I have 2 grams of hydrogen. 1 mole of hydrogen, wow, is 2 grams. So that means I have 1 mole of hydrogen, 16 grams of methane. 1 mole of methane is 16 grams, which then gives me 1 mole of methane. Okay, so total moles is going to be 1 plus 1 plus 0.25, 2.25. So if I want the mole fraction of hydrogen, I need the moles of hydrogen divided by total moles. And when I do that, I get that the mole fraction of hydrogen is 0.44. I could also find the mole fraction of nitrogen, right? I'd put moles of nitrogen divided by total moles. Mole fraction of methane, moles of methane divided by total moles. All right, so now we want to calculate the pressure of the gas mixture, so the total pressure of the gas, and the partial pressure of each constituent gas, if it's 5 liters at 20 degrees Celsius. Well, if I want to find the pressure, and they give me a volume, and they give me a temperature, the only thing I'm missing is moles, but hey, I already calculated my total moles. I've got moles. So I know P is going to be 2.25, ideal gas law, or constant, temperature divided by volume. And I get 10.8 atmospheres is my, I should do this. That's my total pressure. Now I want the partial pressure of each constituent gas. Well, I know that from up here, I know that the pressure of a gas is going to equal the mole fraction of that gas times the total pressure. Well, I know the mole fraction of hydrogen, so let's do hydrogen first. So the partial pressure of hydrogen is going to be the mole fraction of hydrogen times the total pressure that I just found. And that gives me 4.8 atmospheres. Pressure of hydrogen is going to be 4. So of this 10.8 atmospheres, 4.8 of it comes from hydrogen molecules ramming into the walls of my container. All right, so now I want to find the pressure. I should get rid of that box. The pressure of N2. Well, what's my mole fraction of N2? It's going to be moles of N2 divided by total moles. So my mole fraction of N2 times the total pressure. And that gives me 1.2 atmospheres. And lastly, the pressure of methane is going to be the moles of methane over the total moles for my mole fraction times the total pressure, which that's the same as the math for H2, 4.8 atmospheres. Now we can check, now that we've gotten all the partial pressures, what should they add up to? Should add up to the total pressure, and sure enough, 4.8 plus 4.8 plus 1.2 gives me 10.8. Okay, so there are my partial pressures of each thing. Okay. I said another way to think about partial pressure is to think about if that gas particle was the only species in your gas, how much pressure would be exerted. In other words, what I could do is if I wanted to find the partial pressure of, let's say, N2, then I could use the ideal gas law. The pressure of N2 is going to be the moles times R times T over V, but it's just going to be the moles of N2. In other words, if I put in 0.25 here instead of the total moles, I'm going to get the pressure of N2 instead of the total pressure. Does that make sense? So if I put in the moles of N2, I get the pressure of N2. If I put in the total moles, I get the total pressure. Essentially, it's just doing this math, but doing it before instead of after. Yeah, so that's another way that you could solve this problem. All right, number 6. A gas container with a volume of 5 liters holds 0.12 grams of chlorine and 0.145 grams of fluorine at a total pressure of 1.8 atmospheres. Determine the partial pressure of each of the gases. Well, we know, let's see, so we know the partial pressure of my gas. Let's say the partial pressure of chlorine is going to be the mole fraction of chlorine times the total pressure. I'm trying to find this guy. I know the total pressure, it's given. Do I know the mole fraction? Sure. Well, I could find the moles of chlorine from that, and I could find the total moles. Well, that's my mole fraction. So, and I don't even need this 5 liters, doesn't matter. So the pressure of chlorine, well, first let's find the moles of each thing. So I have 0.12 grams of chlorine, 1 mole of Cl2 is going to be 35.5 times 2 is 71. Just going to check my math. Okay, which gives me a mole fraction of, or a total moles of 0.00169. I got to find my moles of fluorine gas. Which I believe will be 38 grams. Which gives me 0.00382 moles of F2. All right, so I want to find the pressure of Cl2. Need my mole fraction. Let's find total here first. Just these two added together, 0.00169 plus 0.00382. 0.00551. Pressure of Cl2 is going to be the moles. Cl2 divided by total moles. That's my mole fraction of Cl2 times the total pressure, which is 1.8. And the pressure of N of F2 is going to be the mole fraction of F2 times the total pressure, 4.8. And I get this, I got 0.552 atmospheres, and F2 get 1.248 atmospheres. Just check my answer. Yep, that's what the answer keys got. And sure enough, these two add up to 1.8, I believe. Yep. Okay, an unknown, this is it. An unknown gas is pumped into that liter container that's already filled with some oxygen. The unknown gas exerts a partial pressure, so in this case we're given the partial pressure of the unknown gas is 2.3 atmospheres. The total pressure is 11.2 atmospheres. What is the mole fraction of the unknown gas? Awesome. Well, we know that the partial pressure of the unknown gas is equal to the mole fraction of the unknown gas times the total pressure. They give us two of these, and then they ask for the third. Easy question. So I could rearrange this. The mole fraction of the unknown is going to be the partial pressure of the unknown divided by the total pressure, 2.3 over 11.2. And I get that the mole fraction of the unknown gas is 0.205. And that's just a fraction, so there's no units on it. Okay, so here you've been introduced to partial pressures of gases and mixtures, and you've also been introduced to densities of gases.